0 infinity R3 t equal to 0. So they want us to show G and H have compact support. So that means, so in other words, so there exists, there's a say, I have R here. So I don't want to confuse with this R, so provide you M by positive, such that G of X will be 0 for X bigger than M, and the H of X will be 0 for X greater than M. So compact support means outside the compact set, or outside the ball, is all 0. So that's really what this means. And then what they want us to show, this is what they want to show, that the solution UXT is less or equal to C over T. Yeah, it's a recording. Well, for all X belongs to R3 and T greater than 0. So I want to show this one. So of course, we have to, the hint, use the representation formula for the solution in 2.4.1, right? I actually did not do any kind of hint. Really, my hint is really not really hint. But anyway, let's look at formula 2.4.1. What's that? So the formula 2.4.1, it is this formula. Okay, one moment, it's here. What do I mean here? So for formula 22 on page 72. Oh, here, this one. So the formula, okay, so from page 72, formula 22, U of xt is equal to, now, this is bar here. This means average. This means boundary. That's xt. T, h of y, to that point y, plus g of y, plus d gy dot y minus x, and then this is the function you are going to integrate, but you are integrating on the boundary of this ball. So it's the surface integral s y. Okay. So this is y. This is from 22. Okay. So let us understand what this means. So if I look at, the formula for that is in appendix. So if I look at appendix, I give you page number is it is A3, page 700. So I have actually 702. It's this formula. So it's formula, page 702. Yeah. So it's equal to 1 over n is 3, alpha 3, R2. And this, I want to make sure, okay, so this R actually is, in our case it will be T. In our case it is T. So T is T here. Page 702, formula 4. VI6, I'm sorry, VI6. This one, integral, integral on the boundary of x t and our function f. So this function thy. So this here's one here. Somewhere too dark here. We have bar here. xt. So xt here. And this is a very special number, but basically this is the surface area of radius t. So in R3, so this is what. So this whole thing, this number is really 4 pi t squared, because this is the surface area of a ball with radius t. So this one thing is 4 pi t squared. Okay. So anyway, so I have this one here, and then this is the function plus g of y and plus d gy dot y minus x dsy. Okay. So this equal to this. Right. So we don't worry about. So we don't worry to this. I mean, because this is a fixed number, 1 over 4 pi t squared. Okay. What we worry about is this integral. This integral, because this is what we want to show, c over t, right? Okay. So if I look at this, I have to think, what are they doing here? What are they doing integration? What integral they are doing? So this. So this is really the set of all y, where y minus x, I mean magnitude of this equal to t. Because this is on the boundary. So this is really y minus x magnitude equal to t. It's really this one. So th of y plus gy plus d gy dot y minus x, okay, dsy. So integration over the surface. So if I have a point x here, then I'm integrating over, this is t, over this surface. I'm integrating over this surface of this. That's why I'm integrating surface, only on surface. Okay, all right. Now, h of y, g of y, the real g, whatever they are, they have a property. Maybe they are 0 outside a ball with magnitude, with radius m. Okay, so somewhere there's a ball. So let's say this is origin. 0. Okay, 0 origin. This is radius m. So g is 0 here. H is also 0 here. Outside. Inside it might not be 0, but outside definitely 0. Okay. Now, I don't know where x is. Okay. I do not know where. But let's say this is x. Let me say this point is the x point. Okay, x point here. All right. So now y minus x equal to t, right? So say this is y. Say this is t. And so y could be where? Y is anywhere. Here. This is the trace of y. This is where y is. Y is on the boundary of this. Okay, because y minus x equal to t. But keep in mind, t is expanding. T could be expanding, and x could be anywhere. I mean, we just don't know where x is. X could be anywhere. But no problem, because this circle and this surface either intersect this ball, I mean this ball, or it doesn't intersect. But even if it intersects, say if it intersects, this area is finite. This area is definitely no better than the surface area. No matter how you intersect this, okay, this could be here, and of course, if when t expand, it could be like this, and then t expand, it could be like this. But no matter how it intersect, the surface area that this ball intersect is no bigger than the surface area of this ball. So therefore, the key point is that if I pick up something from the where H, G, where they are not zero, but the domain is only a portion of the surface area of this guy, of this M. Okay, all right, and then you are going to use this to show that, so that's just the rest is the same. Just look at the first term. Okay, simplest one, the first term. So if I look at the first term, I can bring this t out, right? T, because this is d on y, on y, on the point y. It has nothing to do with t. So let me bring the t out. Now this thing, okay, either this never intersect this. For example, if my t is small, then it could be here. It never intersect that, and in this case, this is 0. But in case it intersect, this thing is no bigger than the surface area of this guy, no matter how you intersect. So this value is a fixed value. Even though I have x and t are arbitrary, it looks terrible. X and t are arbitrary. X could be anything, t could be anything. But either they intersect the ball where the function has no zero value, has non-zero value, or they don't intersect at all. In that case, it's 0. But if it intersect, it's no bigger than that. It's all here. So this is really, this guy itself. We don't look at t. Okay, this guy is less than a constant. This constant is the maximum of this times the constant of the surface area of this already given one. So which is 4 pi m squared. So this one is no bigger than this, where c is the maximum for h. C is the maximum for h, which we already know because this is compact support. So that's what we will see. Some number, fixed number. So okay, so I have a t, but t. So for the first term, I have a t, no problem. K cancel with this t, and this is a fixed number. The same thing for each term. It do the same argument, and so that's why this coming out. This t, this only one t is really because of this t. So make it just one t because of this. All the other actually is 2 t squared, but this term with this term is just 1 t. But what this says is that the wave equation decay, the soup of the wave equation decay like 1 over t, like 1 over t. So the magnitude of the amplitude of the solution of this wave equation is decaying. So this will approach 0 as t go to infinity uniformly. That's the important thing. Okay. So in 3 dimensions, okay. So if you shout to people, no matter what you say, we predict, okay, your voice is going to decay. As time goes, will be decay at the rate of 1 over t. Or even better, if you don't have, but probably you have, because you have to use force, screaming. So when you shout, yell at the people over Johnson Center,